My name is Kara, and I'm with the Ohio LTAP Center here at ODOT, and I'll be your host for this webinar. Today's webinar is Investigation of Pavement Performance in Historically Underperforming Regions, and we are thrilled to have Eddie Chu, Jason Walensky, and Katie DiCarlo as our presenters today. Before we begin, I'd like to cover a few housekeeping items to ensure a smooth webinar for everyone's experience. If you have any questions during the presentation, please use the questions panel on your screen. You can type your questions there, and we'll address them during the Q&A session at the end. If you are experiencing any technical difficulties or have any other issues, feel free to use the chat panel to communicate with our team, and we'll do our best to assist you. Please note that this webinar is being recorded, and the recording will be made available to all registered attendees after the session. A PDF copy of the presentation is available for you in the handouts pane of your screen. All right, with that out of the way, let's get started. It's my pleasure to hand it over to Eddie. Eddie, the virtual floor is yours.
Thank you, Kara. We would like to thank you for your presence at this webinar. We first also would like to thank the Ohio Department of Transportation for sponsoring this research project and the support and guidance from the Technical Advisory Committee and ODOT Office of Research Section. As Kara mentioned, today's presentation will be co-presented by myself and Jason Walensky from Asphalt Institute and Katie DiCarlo from the Heritage Research Group. A quick outline of today's presentation will discuss the problem, the background of previous research efforts, the approach to solve this for this research project, and the findings, and followed by conclusion and recommendations. The problem that was presented is pavements in some regions of Ohio have experienced significantly faster deterioration than the statewide average. Particularly District 3 has the worst historical performance, as you can see on the chart on the right. However, adjacent counties also have had poor performance. ODOT expects its hot mix asphalt overlays to last around 12 years before reaching a PCR score of 60s. And District 3 on average reach about 3.5 years shorter than the expected lifespan. So this leads to significant performance loss and resulting in increased time and cost to maintain the network. So the objective of the research of this project is to determine the root cause of the problem, estimate the financial impact, and assess the cost benefit of potential mitigation measures. ODOT uses a pavement condition rating system to assess the pavement condition. PCR, as it's called. It's a score from 0 to 100. Its value is derived from visual inspection. And the rater identifies the severity and frequency of a specific distress and record its severity and extent. The difference between functional versus structural distresses are also noted. As pavement deteriorates, its PCR score goes down. So a higher PCR drop a year indicates faster deterioration. And faster deterioration means poor performance. ODOT have collected data over the years, and these data enable the researchers to track PCR score and individual distresses. And those distresses, as mentioned, include functional and structural. And those structural distresses and functional distress are shown in the table below. This is an example for a flexible pavement. There are 13 different distresses. Some of them are functional, the others are structural. The example shown on the right is for particular pavement sections where both the PCR and distresses were tracked over its history. And here there are two projects performed on the given pavement and their performance after their treatment. District 3 has historically have a higher average PCR drop after activity 50, which is overlay without repair, and activity 60, which is overlay with repair. And that's the primary rehabilitation treatment that ODOT performs. Average PCR drop per year, statewide, it's about 2.5 points for priority system and about 3 points for general system. As you can see in this chart, District 3 has a much higher average PCR drop. The issues has been researched in prior projects. In 2006, statewide initiative 5 was conducted, and ODOT decided to move the District 3 asphalt mixes from Marshall design to super paved design in effort to minimize the use of poor quality gravel aggregate sources. Aggregate quality was also found to impact pavement performance in other research projects conducted by ODOT. In 2017, Office of Pavement Engineering conducted a review and found underperformance issues still exist. And the effort was initiated to set minimum virgin binder content to improve pavement performance. In 2020, again, Office Pavement Engineering review could not identify correlation between performance and material suppliers. So a deeper dive into identifying root cause was suggested, which leads to this research project being developed and executed. We'll talk about research approach consists of the following steps. The first is to compile and organize data available from ODOT. This includes data from both the Office of Materials Management and Office of Pavement Engineering. As you can see, that include pavement condition, PCR and distress, project history, treatment activity, and year the treatment was performed, and also roadway inventory data and material information such as job mix formula, producer supplier code, aggregate sources, and material quality data. After the data were collected, data mining was performed to identify likely causes. We compared the data statewide versus a focused area of District 3, 5, and 11. We then verified the likely causes through forensic evaluations, and we core the samples and conduct laboratory testing. Geological investigation of aggregate sources was also conducted. And then the financial impact of this underperformance problem was estimated. And mitigation measures were formulated and evaluated, and cost benefit and sensitivity analysis of those mitigation measures was conducted. So we're moving to research findings. So in order to identify the poor performing projects, we set the criteria to look for average PCR drop greater than 4 points a year, and find pavement projects that has been in service for at least 5 years, because initially pavement could be not moving, not deteriorating, or some of them deteriorating very quickly due to some mismatch of the data. Most projects we found that greater than 4-point drop a year are general system pavements, and very few are on priority system. So our focus was on general system pavement. But you can see from the map on the right, the southern part of District 3, many projects were identified to experiencing underperformance. Those counties include Richland, Ashland, Wayne counties, and very few are in northern District 3 counties. And some underperformance projects also are found in District 5, 11, including Knox, Holmes, Coshocton counties, and very few projects in Western Ohio. So the reason for that, obviously, the Western Ohio aggregate sources were primarily limestone, whereas Eastern Ohio are dominated by gravel aggregate sources. And previous research showed that the aggregates something lost, shown as in darker colors, are particularly in District 3 and 4, those areas. As a result of the previous work and ODOT's initiative, the graph below shows that the current approved aggregate sources, as you can see that the chunk of the District 3 do not have any approved aggregate sources anymore. So once we collect the data, we use multiple machine learning methods to perform the data mining exercise. And random forest method was identified to have the better performance in terms of lower error in predicting PCR drop. The random forest method is a decision tree-based method, and it provides a feature importance chart to tell us which parameters are most important in predicting PCR drop. The variables as shown here are listed for data mining. And using the statewide data, this is the so-called feature importance chart that shows that the top parameters that impact PCR drop includes specific gravity, microdeval loss, and LA abrasion, as these are the aggregate related parameters. And also ADT truck number, which is related to actually not the truck number itself, but the specification ODOT used for different truck number. And then the third group is the year before the treatment, the structural deduct, the pavement condition, overall pavement condition, and the other deduct. So these three are important in terms of the existing pavement condition. When we use District 3, 5, and 11, different variable rise to the top. In this case, aggregate absorption is become the top variable. The other variable remained essentially the same. But in this case, the specific gravity and microdeval loss dropped to a lower importance because in this district, there's no significant difference between the specific gravity and lesser difference of these two variables and microdeval loss. Aggregate absorption was taken measured at the aggregate source. However, because many aggregates may be included in a specific job mix formula, and multiple job mix formula could be used in a project. So it's difficult to actually connect exact aggregate absorption versus the actual performance. so the condition prior to the overachievements, such as the structural deduct and overall PCR, and even other deducts, remain important in predicting the performance after overlay treatment. So we also looked into the aggregate sources. We found that the aggregate sources connected to different project performance after the treatment of activity 50, 60, and 38. And it's shown on the last column here, a couple of aggregate sources, such as this 04202 and 42128. The projects use the aggregates from these two sources. 85% of those projects end up being poor, or 11 out of 13, or 14 out of 18, which seems to identify these aggregate sources are of poor quality. But when we take a deeper look at it, this one shows one of the sources, one is the other one. The performance seems to be impacted by where the project is. As you can see here, project in Huron and Morrow County, even though receive aggregates from these two aggregate sources, their performance was not entirely poor, right? So there was actually average performance between PCR drop 2 to 4. So with that, we also did the field visit and testing and laboratory testing. I'll hand over to my partner, Katie.
Great, thanks, Eddie. In the next few slides, I'm going to kind of give a high-level overview of the approach or methodology that we followed to select kind of which pavements we'd go investigate further, given what we've learned up front on the data mining side, to then try to narrow down which sites we're going to target to go and do a deeper dive or forensic analysis. And so our primary focus was on general system routes, and looking for pavements that had underperformance as defined by having a PCR drop of 4 or more points per year. And so the graph on the right side shows those roadways in red, mostly clustered within District 3 and those adjacent districts. Now, when some of the requirements that we tried to keep in our mind when narrowing down which projects we were going to select to go do a deeper dive, we want to ensure that they kind of fell within those districts, that they had some sort of remaining service, that they weren't just recently overlaid, targeting a 7 to 11 year-ish in terms of payment life, and also wanting to avoid any sort of projects that had kind of short sections, and that would allow us to take multiple cores or multiple sections along a project to try to get a better understanding of kind of variability within a project. Next slide, please. So with that, we narrowed it down to 8 projects that fell within kind of 6 different contracts, if you will. They were predominantly in District 3, with 1 falling in District 5. They were a mix of flexible and composite pavements, and we looked at kind of sampling at multiple locations within a roadway segment. We looked for kind of varying surface conditions that either align with the distresses from the PCR data to try to understand what was driving those scores, or maybe underperformance. We took cores, in total 12 from each project at 4 different coring locations, and then brought them back to the lab for further testing. Now, there's a lot on this slide to unpack here, but my goal is really to try to highlight and walk through the 8-step process that we followed when scoping out projects prior to, during that site visit, and then following the site visit. And so really the first step before stepping foot on the project was to evaluate the PCR kind of before and after its treatment or most recent treatment, and look at variations across that project and try to understand what were those primary distresses that were given the highest deduct value in terms of your PCR score. The second step was to review construction plans, trying to understand what were typical sections that we should expect to see. Were there multiple different sections? Was there widening that happened or took place during that most recent treatment. We then looked at project JMF and material data and kind of compared that against information that we received from ODOT, as well as paired that with any QC results that were available from those projects to try to understand variability during production. And then step 5, we looked at evaluating any density data. So if there was cores and density data that was available or nuke gauge data, try to understand how well was that pavement constructed. And so really steps 1 through 5 all take place before even stepping foot on that project site. Step 6 is where we get into the field and we document any distresses that we observed. We take our cores, we look at underlying layers within there, at drainage, try to understand, is the distress in the wheel path, is it outside of the wheel path? And that kind of helped guide step 7 as we randomly selected different locations within the project segment to core. And that was dependent on the pavement type, if it was flexible or composite. We tried to take cores both kind of in both travel lanes, if you will, and within the wheel path and outside of that wheel path. And then step 8 was taking those cores back to the lab, bulking them all first, measuring them, doing an inventory of those cores, and then subjecting them to a chemical extraction where we got AC content and then ran gradations after. There's a lot of detail there and certainly can all be reviewed in the final report, but I'm going to turn it over to Jason to talk a little bit more about some of the trends and observations that we found.
Thank you, Katie. First off, I'd like to describe how we took a very deep dive into the pavement condition ratings for each of those 8 pavement segments across those 6 contracts as part of the analysis. So here's an example from a segment of State Route 603 in Ashland County. This is the segment from 7.48 to 11.57. So a segment across the large stretch of pavement there in Ashland. Just some understanding around how we use this data and what we were particularly looking for. So first off, just like to point out, these are different projects that were constructed across this segment of State Route 603. We have an activity 60, which is an HMA overlay with repairs that was done in 2005. We then have another project that was also delivered in 2014. Now, between the 2005 and 14 project, you can see the PCR score dropping over time as distress increases. In this case, Professor Chu mentioned we're looking at structural distress. Those are the distresses identified in the bottom portion of that chart. Notice they have the hatch there. Those are distresses that, based on their description, are deeper into the pavement. They're contributing to distress in our newer overlays going on top, whereas some of the functional distresses identified with solid colors, those are going to be more related towards the aging of the asphalt pavement, the sealing of the asphalt pavement, low density, high air voids, distresses that are more typical to surface related distress. So our first analysis was, let's really take a deep dive, understand what the projects, how they performed, what distresses were progressing more rapidly than others, but also be in mind of what did we build the existing contract upon. And in this case, we had a very poor condition, again, mid-50s, very high in structural and functional distress. And again, we didn't realize very good performance with this activity 60 constructed in 2014. It reached 60 only 7 years later in 2021. So moving on, these projects very large, in length, and oftentimes these projects had multiple typical sections as part of the construction. And just for reference, we'd like to, just show a project on State Route 511. Also in Ashland County, that project had 3 typical sections. The first typical section highlighted in gray there in the table, I think that was an urban section. It was an 1.5 inch pavement mill followed by an 1.5 inch 9.5 millimeter 446 type A overlay. The large portion of that project was typical section number 2, again very similar to section number 1, consistent 1.5 inch pavement milling prior to the 1.5 inch overlay going back on top. The one of interest in this particular project is typical section number 3. So we had approximately a 2.5 mile section towards the end of that segment. It called for variable thickness milling ahead of the overlay. So that mill cut 1.5 inches deep at the center line. We removed more material out towards the pavement end up to 2.5 inches. So we took more material off across the width of that pavement. And then once that pavement was milled, a slightly thicker overlay was put on top in 2 lifts. So we did a 2-inch lift. It was a 3/4 inch intermediate, followed by an 1.25 inch surface mix going on top for that section. So we wanted to take a look at those different typical sections. In the bottom table, you can see the gray, the white, and the blue noted versus the straight line segment markers there in the pavement, and then identify and look at how the PCR changed over time within those segments. And it was interesting to us that even though that blue section, we had a little bit deeper mill to remove more material and a slightly thicker overlay on top, it did not realize much of an improved performance against the adjacent section that even had an 1.5 inch removal and 1.5 inch surface. So despite the typical section in this case, we did not realize any enhanced benefits when it comes back to performance. Moving on, just like to share a couple of the pictures and the cores that were collected on our field visits. Here's a picture that was collected from State Route 603 in Richland County. And this was very typical of the distress that we saw on many of the projects that we were visiting. A lot of times we had transverse cracking, and you can see in the core pictures that these were typically full depth throughout not only the overlay activity 60 project that we were investigating, but actually extended through into the underlying layers. And if you notice the middle and right core in that bottom picture, there's no mix below the surface and the next layer, because that material was disintegrated, can actually be recovered out of the core hole. So just an idea of the existing pavement conditions that we're dealing with when we're looking at these activity 60 projects in District 3 and nearby. Also saw a lot of issues with longitudinal cracking, particularly in and around the center line, typically associated with low density perhaps. Very common to be found to be top down, particularly in those areas. And again, this is an example from State Route 603 in Richland County. Moving on, this is another photograph collected from State Route 42 in Ashland County. This is a composite pavement. This surface was originally placed back in 2013. Another recurring observation that we saw across many of the projects was the issue of debonding. Surface layer, intermediate layer from the underlying pavements. So you can notice here in the center core, as well as that core on the right, we were not able to extract a full thickness, flexible asphalt pavement sample above the concrete. Oftentimes, we saw that the surface layer or the new layers would debond. This definitely impacts the structural performance of pavements long term, can help facilitate cracking both in those new layers, both top down and bottom up direction. So again, just some context that we saw this recurring theme across the projects that we visited, debonding a major issue. And again, here's this a photograph collected from State Route 511 in Ashland County. Just take a note of the distresses on the pavement and the cores that were actually cut and collected from this segment area. Again, you can see the cracking extended throughout the newer overlays that were investigated, but those cracks definitely extended through the underlying layers, impacting the ability of that surface mix to perform. A lot of times those underlying layers severely distressed, and maybe even some stripping that was realized there in that center core. You can see that material disintegrated, loss of integrity, loss of stability, which definitely impacts the ability of our overlay to perform as designed. And another recurring theme, and I think this is more of a sign of the times, particularly when these pavements were constructed, but longitudinal joints on these projects definitely were a big impact on the pavement condition rating and the performance. So here is a shot from Ashland State Route 545. This is one of the additional pavements that was asked to be investigated in an addendum part of the work. We can just see the disintegration of that longitudinal joint enables water to enter the pavement. We all know that water entering the pavement, particularly freeze-thaw cycles, contributes to potholes, other distress. Again, another significant recurring theme across these projects is the poor quality of the longitudinal joints throughout the projects. So of the 6 projects that we visited, a lot of them had similarities. You know, 5 of the 6 projects, when they were constructed, less than 60 PCR. Oftentimes the condition of the pavement could have been in the mid to low 50s. So a very, very distressed, poor quality asphalt pavement. And despite the condition of that asphalt pavement, the amount of asphalt that was going on top of these pavements relatively thin, often less than 2 inches, unless it was one of the case like 511 where there was a very thin intermediate applied. We're looking anywhere from 1.25 inch, 1.5 inch surface typically applied on these heavily distressed pavements, oftentimes with some identification for full and partial depth repairs. We also noticed that, you know, when milling was prescribed in the contract documents, you know, we didn't mill very deep into these pavements to remove some of the heavily distressed surface layers, the historically distressed intermediate and surface layers. Typically, again, we're looking at 1.5 inch milling or less. Again, not getting very deep into the pavement to eliminate some of that distressed materials. And as I mentioned with the instance of 511, even when we had slightly thicker asphalt overlays, typically that did not lead to improved performance. So I'm not sure if the conclusion is more asphalt gives more performance, especially when you're putting it on existing asphalt pavement that's heavily distressed. We spent a lot of time reviewing the quality control data, both the field quality control data as well as the quality control data coming out of the QC labs. Starting with the field quality control data, we wanted to understand the quality of the construction of these projects, and the best way, in my opinion, to measure that is to look for our density results and understand what the in-place air voids were on these projects constructed. It is noted that 4 of the 6 projects that we looked at followed 446 core density for acceptance of the surface lift. And for, I would say, the majority of the lots across those 4 projects, they did realize a pay factor of 1 or higher. So they actually realized really good initial density, low air voids. But despite that, those projects actually experienced poor field performance. It is noted 1 project, 1 segment, there was a deduction in density. And when we looked at the PCR versus that lot, we noticed that, again, it is at poor performance, a lot of functional distress related with low density, raveling, other surface related distresses. We spent a lot of time in digging in the quality control data for each of these projects so that we could actually compare the results to the lab testing that was done after the retrieval of the field cores on these projects. So the first thing we really wanted to understand is, was there an agreement based on the QC data where we took the lot, tied that back to the location so that we could match the QC lot data to the core that was collected from each project. One of the findings that I thought was very interesting was the AC content typically reported in our TE 199 results. We had very good agreement when it comes to asphalt content from our extractions for those cores recovered. And I make that comment despite the difference in test methods. We were doing a chemical extraction of those cores to measure asphalt content. I would say the biggest surprise that we saw in comparing the quality control data to the results of the field cores collected and tested was in the aggregate gradation results. And I offer this table for consideration. So we report the percent passing the number 200 or the dust content from the job mix formula. Then we take the percent passing 200 reported in the quality control data for the lot that was closest to the location that the core was collected. And we can see that from QC to JMF, we see a slight increase in percent passing the 200. But what we found very interesting is when we looked at the percent passing the 200 for the cores that were recovered after chemical extraction and washing, we saw a significant increase in that percent passing 200. And when you take that result and you compare that against to the, I'm going to say, extraction results, we can see that fines to asphalt for the total AC in this case, that number is pretty high. And it is recognized by industry that when you have a very high fines to asphalt ratio, that can lead to durability issues. More so, we want to compare dust content to effective AC. Effective AC is the asphalt that remains around the aggregate particles that is not absorbed into the aggregates during production and service. So I think if we looked at effective AC, those numbers be even higher. So definitely raise some questions and going to be coming back in our recommendations later on. So the projects that we looked at, also recurring theme is, you know, the immediate past project also realized underperformance. And, you know, based on this, I think we're suggesting that the activity 60 that's selected for treatment here, it's not thorough enough to address some of the underlying issues. And I offer this photograph that was collected on one of the sampling trips. You kind of see the area down to the lower right looks relatively distress-free. That's probably an area that was full depth patch on the edge there, but look immediately adjacent to that towards the center line and the adjacent lane. Again, those distresses probably heavily impacted by underlying condition of the pavement, just can't address all the existing issues that remain by picking and choosing areas with full depth patching. So probably a more permanent solution might be best for long-term performance. Particularly in District 3, we did not see any maintenance or preservation on these roadways whatsoever. Something as simple as crack sealing can really help seal up some of the crack as they develop, keep water out, help minimize distress. We did not see any of that on the projects that we sampled in District 3. I'm going to turn it back over to Dr. Chu to discuss the financial impact of the underperformance realized in these areas.
Thank you, Jason. So we looked into what is the financial impact of this underperformance issue in order to quantify the scale of the problem. So we calculate the financial impact by multiplying the length of pavement section to the increase in equivalent annual cost, which is expressed by a pavement, whether a pavement is shorter than a 12 years expected life. If it's pavement section that lasts less than 12 years, will incur some financial loss. So it's also proportional to the number of miles of underperforming sections in each district, and it also influenced by the district-wide average rehabilitation cost. So the table on the right summarizes this financial impact result study that shows that overall the statewide each year, about 39 or close to 40 million financial impact were caused by the underperforming pavements, of which District 3 alone, it's about close to 12.72 or close to 13 million a year. It's about 1/3 of the loss came from District alone. So a deeper pavement treatment, as mentioned by Jason, could reduce the impact of existing underlying distress on future overlays. So deeper mill and fill strategy could be considered. This include remove existing stress and unbound layers and include full depth repair if warranted. And other technologies such as full depth reclamation or cold in place recycling could be considered. And ODOT has recently performed the full depth reclamation. The benefit of implementing the mitigation measures can be calculated based on the savings that will be realized in terms of reduced future rehab cost due to improved pavement performance and longer surface life. So the figures shown here represents the current situation where the pavement will last 8 years and repeatedly may need the rehabilitation. And in this case, the service life existing a subsequent overlay is assumed to be about 8 years. And if a deeper treatment is performed, and this is just an illustration that the longer performance can, or pavement lifespan can be accomplished, which will require fewer future treatment. And so given a estimated total planning horizon is 30 years planning horizon, we can see only a little bit over 2 treatment would be required versus more than 4 treatment, or about 4 treatment would be required. So if we put that into a table, as we see there, planning horizon of 30 years with the service life, assume this case 14 years of the deeper treatment. And subsequently, it will restore the activity 60 or 50 treatment to 12 years of service life. Then if we go to the further right, we see the deeper treatment will be equivalent to about 2.42 of the typical overlay treatment. Given a planning horizon, longer planning horizon, such as 60 years, and then they will be equivalent to 3.67, which means given the average activity 60 cost is statewide, it's about 220 grants. And if we multiply that by 2.42, the break-even cost of deeper treatment for a 30-year planning horizon, it's about 532, which means if the cost of the deeper treatment is less than this, it will be justified. And for a longer planning horizon, you could even justify higher cost. So with that, I will return that back to Jason.
Thank you, Dr. Chu. Here at the end, we're going to go through the 8 recommendations that the research team offered to the department based on the findings of our research effort. So let's go ahead and get started. Recommendation number 1 is where applicable and where economical, let's try to address existing structural distresses before any asphalt overlay resurfacing. And again, this goes back to trying to identify and remediate any of the underlying distress, stripping, cracking that is occurring in the existing pavement structure. Let's try to minimize the impact of that distress from reflecting or contributing to the performance of our brand new asphalt overlays. And with that, let's be very mindful that we are getting an adequate bond with our new overlay. That's best practices when it comes to cleaning milled surfaces, eliminating any scabbing that happens from the milling process, getting and applying adequate tack coat. Let's get good bonds so that we're not getting any debonding and that we're able to actually transmit the stress and strain of our traffic all the way throughout the depth of that asphalt pavement layer. We make this recommendation with the fact that even though we might have slightly thicker HMAs, that did not lead to extended performance based on some of the field investigations that we had. So let's try to address those underlying issues where they remain, again, to give our overlays the optimal ability to perform over time. Recommendation number 2 is based on the process in which we were able to take all the data from the different offices, pavement engineering, materials, quality control data from construction. And our recommendation is actually to monitor data in a systematic and integrated way. Within the research and development, we've put the framework recommendation together to develop a tool that can actually link pavement performance together with material input data, as well as construction information together in one place. This would help ODOT and future researchers identify projects that have poor performance, and you can really aggregate the material tied with it, including JMF information, material source information, quality control data, really to help understand other impacts on pavement performance long-term in a much easier and facilitated way with the amount of great data that ODOT's collecting. Our third recommendation, again, this is based on the analysis that Dr. Chu just went over, is let's evaluate our historically poor performing segments. So those pavements with previously poor projects or even multiple previous projects, let's consider those for the deeper rehabilitation options, particularly if the structural distresses are those that are coming back relatively quick, 5, 6, 7 years, particularly in these areas of focus, 3 adjacent to 5 adjacent to District 3 as well as District 11. We've realized based on these project analysis that Activity 60 is not adequately solving all the pavement issues, so maybe deeper solutions, although costing more today, create value long-term for ODOT, especially if we get better long-term performance of our overlays, minimize the construction cycle, get those asphalt overlays to last up to 12 or even more years if possible. And one of the tools that may help ODOT realize that is both full depth reclamation and CIR. We did acknowledge deeper mill and fills as one option, but these technologies, full depth reclamation, CIR, they are rehabilitation methods that can be used to address underlying issues. FDR will go through the entire thickness of a flexible pavement. We can grind that pavement up. We're going to stabilize, glue that back together, eliminate any distresses, cracks, stripping issues, glue it to provide a solid foundation for our asphalt overlays going on top. CIR is very similar. We're going to use a modified milling machine. We're going to go anywhere from 3 to 5 inches in the pavement. We're going to mill it up, add a stabilizing agent, pave it right back in place. Again, that's to help with some of the distressing and the underlying layers before we put our asphalt overlays on top. We offer these suggestions with the realization that there is a cost benefit with these technologies versus removing and replacing the materials on site with all new imported material. Our fifth recommendation is to actually establish a pretty aggressive preservation and maintenance strategy. I offer that particularly in District 3. Something as simple as crack sealing can make a big difference when it comes to performance. Again, centerline joint deterioration, pretty widespread issue across the district on the pavements we looked at. There are other material solutions around the centerline joint to help minimize that distress, water intrusion that can severely negatively impact the ability of that pavement to perform. A little later on in life, we can put some topical treatments on these asphalt overlays, whether that's an ultra thin overlay, depending on the traffic volume, could be anything like a chip seal, maybe it's a micro surfacing. Again, applied at the right road at the right time, really to extend the functional life of that asphalt overlay. Typically here in District 3 that we learned that these pavements were performing so poorly they actually couldn't get in that preservation queue, if you will, because they were dropping so fast. So I think we can solve some of the distress issues, build a good overlay, get a preservation strategy put together, really extend the life of the pavement, we can get much longer life out of our HMA overlays. Number 6, we recommend ODOT to take a look at the issue of concerns when it comes to mixed production and aggregate gradation data. And this again ties back to the finding where we had much higher fines content versus the quality control reported data and the JMF based on our field investigations. You know, we also heard some feedback, particularly from the district materials lab, that it would not be uncommon for density cores being sent back to the lab to be visible aggregate breakdown in those cores. Might be over compacting, damaging the aggregate structure and in turn the performance. So we highly recommend to take a look to really understand what's really happening. Maybe this was a anomaly occurrence based on the sign of the times, but I think this is something that can directly impact durability of an asphalt pavement. So putting a project together where we look at sampling location, the test method to understand what the percent passing the 200 is, and really getting fines to effective asphalt dialed in production, I think could help shed some light on the durability issue with some of these areas and projects. And in light of the fact that we're dealing in an area with high absorption, particularly in the southern end of District 3, we also recommend ODOT to consider specifications targeting not total asphalt content, but rather effective AC content. This would help the department and contractors use aggregates in a little bit different way. If it's a higher absorptive aggregate, it's going to pull more asphalt content into the pores. That results in less asphalt around the particles, thinner films to glue the aggregates together. They're going to be more prone to accelerated aging, and in turn, the functional distresses that come with that, raveling, top-down cracking. So looking at the impact of absorption in both the JMF and production is recommended. And we also make the note for ODOT to consider verifying GSV of plant-produced mixes. We recognize that they've made some improvements in specs recently on VMA field requirements. It may be worthwhile to also verify some of the GSBs to understand variability of aggregate-specific gravity and absorption during production. And our final recommendation is let's prioritize 446 acceptance testing on coring rather than nuclear gauge, particularly in these underperforming areas. It's much better, it's much easier to track data based on cores rather than gauge. We recognize holistically as an industry that better density gives us better improved performance. And I think when we think big picture about how we combine construction data back to pavement performance, this would make it a little bit easier to understand how the asphalt pavement was constructed and put some better lab numbers around that rather than relying on the nuclear gauge for density documentation. So with that, on behalf of Dr. Chu and my co-presenter Katie DiCarlo, we'd like to say thank you for the time and attention today on our webinar.
Thank you so much for that insightful information and presentation. We're now going to move on to our Q&A session. We have 2 questions right now, which works out well because we are going to try to stick to our end time of 2 o'clock. So for our first question, we have, were the subgrade soil borings or base conditions investigated?
Yeah, that's a good question. We did, when we went and did some of the coring, some DCP measurements were collected, but we did not see any, I'm going to say, significantly low DCP results in those subgrades. Nothing of high concern, especially with the thickness of the asphalt pavements that were realized on these projects that were visited.
All right, thank you very much. And for our last question of the day, if the aggregate is an issue, Will reusing the materials in place really help the rebuilt pavement?
So to help understand the question is, if we have an aggregate that may be impacting the quality of the surface, is it going to negatively impact how we reuse it later on? And I'm going to rely on the answer. It depends how we use it. So when we want to use it in a recycling application, I think we can handle and design with that wrap appropriately. And in turn, when we consider some of the in-place recycling technologies like FDR or CIR, you know, we have to account for the properties of those materials as well in the design. Oftentimes when we're looking at FDR and CIR, those materials are already coated, so we are not necessarily worried about additional absorption. But we do want to understand if those aggregates may be a little more prone to crushing, which, you know, we can adjust with supplemental aggregates in the mixes, for example, to help accommodate that. So it comes back to the engineering, in my opinion, the mixed design engineering when those materials are encountered.
Thank you very much for that. Okay, so I know I said we only had one other question, but we had another one come in. And this question sounds like someone that's pretty familiar with the area wants to know how was 251 and 253 pavement repairs accounted for in this study? They typically have a higher percentage of repairs attempting to address deeper stresses and deterioration in their projects. They didn't see any mention of that. They thought they might see a mention of that.
Yeah, so that's a great question. When we did our project review, we documented and noted where the pavement repairs were noted and identified in the construction plans. It was very difficult for us to go back and see where actual partial and full depth repairs were performed. However, when we did our field investigation, as I showed in that one picture, you could kind of see where some of the patching had been done previously. In the case of that, we did sample in some patched areas or improved areas. We also took samples in the areas that, based on surface conditions, more than likely weren't repaired prior to the overlay. So we tried to get a mix of both. I hope that helps answer the question. There's a little more detail in the body of the report on that one.
Thank you so much for that answer. Okay, well, that is all the time we have for questions today. So on behalf of LTAP and ODOT, I'd like to thank Dr. Shu, Jason Walensky, and Katie DiCarlo once again for sharing their valuable knowledge and expertise with us. As I mentioned earlier, the recording of this webinar will be shared with all registered attendees. And I would just like to ask that if you, before you leave, we'd appreciate your feedback. So there will be a very short 4-question survey that'll automatically launch in your browser once the webinar ends. It only takes a minute, and your input helps us improve future sessions. With that, I will say thank you all for attending, and we hope you found this webinar informative and engaging. Have a wonderful rest of your day.